Once again, I welcome you all to this online teaching. This is a continuation of our discussion on nanoscience. Now we will discuss about the characterization techniques that are used to study nanomaterials. It is not that there are separate techniques available to study these materials. Already whatever techniques which are available to us as characterization techniques, those all can be used to study nanomaterials. If we look the nanomaterials, we may be interested to study various aspects of these materials. I have written some of them here. Like we may be interested to know the size of nanomaterials, or we may be interested to know the shape of nanomaterials. It may be atomic arrangement within a nanoparticle, that is crystal structure of nanoparticles. When we make multi-component nanoparticles, like more than one element we put what we call as a compound material, we may be interested to know the composition of that material, or you may be interested to know various physical properties of nanomaterials like optical properties. Within that, we may be interested to study absorption of light or emission of light after photoexcitation. If the materials under consideration are magnetic in nature, we may be interested to study magnetic properties of these materials. If they are dielectric materials, then interest may be on dielectric behavior, or it may be electrical properties of these materials, and it is not limited, it may include many other properties. So looking at these various parameters which we would like to study on nanomaterials, the characterization technique or techniques, they vary depending upon our requirement. So first let us see the surface morphology, that is size and shape, or the appearance of nanoparticles. That is basically nothing but a direct look of nanoparticles, and that is possible only by the study on surface morphology. So in this regard, when we want to study surface morphology, we need to have a microscope. The microscope is a device which will help us to magnify the image with a good magnification so that there is a good resolution. Hence we can magnify the image to best possible extent in order to have its fine details. One such a simple device which will help us to magnify given object is optical microscope. This is a very simple microscope. You can say it is just a single lens microscope. You have a convex lens, say there is an object, there is an image formation, Either it can be this side or the same side, real, virtual, or it can be inverted image. That doesn't matter. But if I take convex lens, I can try to magnify depending upon the focal length of lens, and ultimately I can try to enlarge the image of given object so that we can look finer details. Though here it has been written in angle of magnification is written in terms of angle subtended by object and image, but you can also take these as the height of object and height of image. So magnification is defined as the height of image to height of the object. So basically it will tell us how much we have magnified the image. If it is a single lens, the magnification is given by 25 divided by f. F is a focal length of the convex lens what you are using. 25 is the distance of distinct vision that is connected to human eye. So this is a simple equation for a simple microscope about the magnification. Then in order to improve certain things, basically magnification and resolution, we can have a compound microscopes where we can try to use more than one lens so that you can have good magnification. Like a compound microscope, what we call, we have objective lens and eyepiece. So in case of compound microscope, magnification is given by two terms, x divided by f1 into 25 divided by f2. I will not go into details of this. This is all you have learnt in basic physics. X upon f1 is nothing but the magnification of objective. 25 divided by f2 is a magnification of eyepiece, where x denotes the distance of image from the focal point. It is not only magnification that is important, because magnification will help us to magnify the image. There are other parameters which also decide the quality of final image what we will have in microscope. There can be distortion, there can be astigmation, there can be aberration and other effects which will try to limit a quality of image. There is one more important parameter that comes. It is the resolving power of a microscope. This comes because of diffraction, therefore it is called diffraction of light due to scattering from the sample surface. So if you work out a mathematical expression for resolving power, that is denoted as R, is equal to lambda divided by 2 into n into sine theta. N is the light what you are using as a illuminated light to look under microscope. The term n sine theta is nothing but numerical aperture. Therefore this becomes equal to lambda upon 2 into numerical aperture. Here R is nothing but the closest distance between the 2 points. So what does it mean? It means how well you can resolve the two very closely sitting points. So it means smaller the R, better the resolution. Means you are able to resolve up to that extent. As I said, lambda is a wavelength of light and n is a refractive index. And the numerical aperture Na is approximately equal to 1. So under this condition, resolving power becomes equal to lambda upon 2. In fact, this is referred as a diffraction limit. R equal to 0.2 micron if we use lambda equal to 400 nanometer. There is a slight mistake here. Okay, if you use the visible light of 400 nanometer and divided by 2 of that is nothing but 200 nanometer, that is 0.2 micrometer. So visible light what we have, it ranges from 400 nanometer to 700 nanometer. Due to all these factors, we can say optical microscope will give us a resolution which is only just a few micron. So few micron, what we are getting as optical resolution is not enough to study nanomaterials size and shape. As I said earlier, nanomaterials are the ones whose size varies from 1 nanometer to 100 nanometer. So the kind of resolution what we have is 1000 micrometer, that is almost 1000 times higher than the smallest size of nanoparticle, that is 1 nanometer. Hence optical microscopes will not be suitable to study nanomaterials. And this limit of resolution is mainly coming from the light what we are using in optical microscope as illuminating light, and the detector is human eye. So the final conclusion here is, hence nanomaterial cannot be studied with the help of optical microscopes. Then the question is, then how do we study nanomaterials? This help came from other kind of microscopes. First we will try to discuss electron microscope. It is called electron microscope because in the place of visible light, that is visible electromagnetic radiation, you can try to put electron beam to do the job. Once again, the basic physics is same, that is resolution is approximately lambda upon 2, that is the diffraction limit. So what we see here, smaller lambda, better the resolution. But if I look visible light in optical microscope, I said earlier, the wavelength range of visible light goes from 400 nanometer to 700 nanometer. Ultimately, if you take this as the limit, 0.2 micron is the resolution, hence optical microscope not suitable. We have to look for alternate microscopes, and the foundation of that is on the basis of quantum mechanics. As we know from the quantum mechanics, one of the basic postulates of quantum mechanics is every quantum particle is dual in nature. We call that as a de Broglie's hypothesis. Quantum particles have dual nature. It will act as a particle, at the same time it also acts as a wave. So it is also called particle-wave duality of all small particles. We know the linear momentum P is equal to h divided by the wavelength. In fact, this we call associated wavelength with quantum particle. So that depends upon the speed of particle. So what we see, P is equal to h divided by lambda. The momentum and associated wavelength are inversely proportional to each other, and hence we can say electrons can be waves. If electrons can be waves, then in the place of electromagnetic radiation, these can be replaced by electrons. Then we can have a microscope, and associated wavelength we can control by application of electric field, because by application of electric field the velocity of electron can be controlled. As a result of that, we can have better resolution. In case of beam of electron, electric and magnetic fields can bend the beam of electrons like optical lenses do for the light. So taking simply the kinetic energy of electrons, that is, you can have electrons thermionically emitted. It means if I take ordinary bulb, heat the bulb to high temperature, we all know there is a process of thermionic emission. The electrons will leave the metallic filament, come out of the material, and this process is called as thermionic emission of electrons. Once electrons come out, you subject electrons to applied electric field so that you can accelerate them the way you want. Here only important is how much electric field you can put across the beam of electrons. So using the de Broglie's relation, you can try to make simple calculation by putting fundamental constant value, that is H value. Applied voltage is 20,000 volts, that is written in terms of kilovolt. Here applied voltage, associated wavelength lambda in terms of nanometer. So I have varied the applied voltage 20,000 volts, 50,000 volts, 80,000 volts, 100,000 volts. Then corresponding wavelength, when you calculate, in case of 20 kilovolt, you have the associated wavelength 0.0085. In this case 0.0053. In case of 80 kilovolts, it is a 0.0041. In case of 100 kilovolt, associated wavelength is 0.0037. If I take even the first one, that is 20 kilovolt, associated wavelength, what we have is 0.0085 nanometer. If I convert that to angstrom, it is a 0.085 angstrom, extremely small wavelength. Lambda by 2, if you do the kind of resolution what we see is extremely large, very, very high resolution. The kind of thing what we see is even you must see atoms very clearly, but fact is other factors also come into picture, other factors which will try to hamper the resolution. But anyway, this clearly shows that in the place of ordinary light, if we use a beam of electrons, then we can control energy, we can try to accelerate them to very high energy. The result of that is we can have very, very high resolution. Hence we can try to explore beam of electron with electric and magnetic fields as lenses, so that one can design electron microscope with very high resolution. Hence that is quite suitable to study nanomaterials what we are talking about. But we must also keep in mind at the same time, at such high energy, 20 or 50 kilo electron volt is quite high energy compared to ordinary light, whose energy is only about 2 to 3 electron volts. You can take it as an average. So at such high energy there can be complicated interaction between electrons and the matter. The beam of electrons what you put on a material, there can many complex reactions are going to happen, and we have to consider them. At the same time, we have to see that material must be stable at such high energetic interaction. Just to brief here, there is a beam of electron which impinges on the surface of material. Then there is a kind of interaction volume. The electron beam enters into the material from the surface. There is backscattering. These electrons, we call them as backscattered electrons. Once electrons go inside, interact, dislodge electrons from the atoms, there can be secondary emission of electrons. We have secondary electrons coming out. Within this, because of interaction, there is Auger electrons which will come out. Therefore, we have Auger electrons. Since innermost electrons are lodged from their inner cells of atoms, the result of that there is emission of X-ray, characteristics emission of X-ray. This all is going to happen when you put beam of electrons on a material, and these also can be explored to have not only just microscope, you can also have important characterizing techniques in this process. So I just close this discussion here.